a kind of cladogram. This is using the format of having them angled branching off, but it's still a branching diagram. The reason, as I said, I like to use this is because these are reasonably familiar organisms, like most of them are. So what we have here is chordates. You might remember from some other course, there's a phylum called Chordata to which we belong. So we have here, if we're interested in looking at relationships within this clade, we have to compare it to something. And otherwise, we can't really tell whether a character is plesiomorphic or apomorphic unless we have something that's not a member of the clade. If all you had was this information, and you knew that all of these had a backbone, which is what a vertebra is, this wouldn't really be all that useful because you wouldn't know what their closest relative was. But if we have their closest relatives, or at least ones that they're using this diagram, these are lancelets. Probably not actually the closest relatives of the backboned organisms, but pretty close. And they have no backbone, and they never did. What that tells us is that there was a transition after this branch point. One branch leads to these little lancelets out in the ocean. The other branch point leads to all the vertebrates. So this is a transition that occurs here. So first of all, vertebrae, the vertebral column, is an apomorphy of the clade of vertebrates. That's a very early apomorphy. In fact, it is a synapomorphy of vertebrates. All vertebrates have a backbone. That's a synapomorphy that can distinguish them from their closest relatives. But what if you're not interested in distinguishing all vertebrates from non-vertebrates, but you want to see, well, how does a lamprey compare to all other vertebrates? Does the backbone helpful in doing that? Does the fact that lampreys have vertebrae tell you how they're related to leopards? Do leopards have vertebrae? Yeah. That means that if you're at this node, what does the vertebrae come? It's an homology, but what type? It's plesiomorphic. It's present in lampreys and this other clade, so it must be a plesiomorphy. On the other hand, and we can continue on up here, we see hinged jaws. Hinged jaws do separate lampreys, which have a circular mouth, from all the other fish and others. Of course, we can do this at each stage. So let's go up to the top here. Hair is certainly an apomorphy of this clade, but it's not a synapomorphy of vertebrates. It's an apomorphy of vertebrates because it is a transition that occurred after vertebrates, but it's not a synapomorphy of vertebrates because not all vertebrates have it anyways. It is, however, a synapomorphy of this branch. The leopard isn't the only organism to have it. What is that a unique characteristic of? Mammals. And it does, in fact, distinguish mammals from reptiles who do not have hair. So hair is a synapomorphy that can be used to separate mammals from turtles. Can it be used to separate leopards from lions? No. So is a given trait character a synapomorphy or a plesiomorphy? You can't really answer that because it would have to depend on what you're looking at. Whether the same trait is an apomorphy, synapomorphy, or plesiomorphy, depending on what comparison one's looking at. The outgroup is simply the comparison sister group that you use to help you work out the relationships within the group you're interested in, which is the in group. So we have our in groups and our out groups. Let's go back to this tree. With one exception, all of the branching in this tree is dichotomous. What is di? Two. Kato comes from a term referring to splitting or cutting. It's basically dichotomous means one splits into two, or one branches into two. That's what dichotomous means. The way we conceive of evolutionary trees, of speciation, of all such arrangements is that they are dichotomous. If we actually know the true relationships, it will always be dichotomous. One branches into two. And certainly this is dichotomous. All of these nodes are dichotomous but one. Which one is not dichotomous there? Which number?
5.
Number 5. So why would that not be dichotomous? Is that because we conceive that one really did immediately split into 3? What does it actually represent? They don't know. The data that they use, the information that they had, which is restricted to what they show here in this study, could not distinguish how these 3 were related. We assume that there are 2 of them in there that are more closely related to each other than the third. It's just that these data don't tell us which ones. I don't know off the top of my head which one is the less closely related. I'm sure through other information, DNA and so forth, they can work that out. But simply using the coloration of the coats, you cannot tell whether it's a jaguar is more closely related to a lion or to a leopard. There's simply, this data set doesn't resolve that. So these types of more than 2 coming from a node simply means the information isn't enough to tell us how they're related. That's called a polytomy. What does poly mean? Yeah, many, more than 2. It's also called unresolved. Means we can't reach a decision. So whenever you see those, that means it's unresolved. The data weren't sufficient to make a determination. All right, the last set of terms before we get into methods themselves, I've put up here these terms in their noun form: monophyly, paraphyly, polyphyly. You probably see them more often in the adjective form. If you drop the Y and put an adjective form, ETIC, that gives you the adjective. That's actually seen more often. So we have monophyletic and paraphyletic and polyphyletic. Few of you I know were in my Biology 102 class, and you might fondly recall one of these test questions where I showed you a tree and then said, is it polyphyletic or is it monophyletic or not monophyletic? Of course, then I always ask the follow-up question that nobody likes, which is what? How do you know? But I didn't make you distinguish in that class between the other 2. This is 339, so we're going to see all 3 of the terms used. And what this involves is the goal of cladistics. It's a method of classifying. Ultimately, when we classify, we put things into groups. A generic term for a group is a taxon or taxa. Mammals is a taxon. So is the cat family, Phalidae, that's a taxon. Animals is a taxon. These are classification groups. In the original classifications that people like Linnaeus made, since they weren't based on any concept of evolution, they just grouped things based on similarity. But of course, since we have evolutionary biology, the goal of cladistics is to try to make the taxon monophyletic. So monophyly or monophyletic taxon is the goal. So what we need to do is see what that means. And what are the alternatives which are not the goals. So what makes a taxon monophyletic, whether it's an entire domain or just a single species? What makes it monophyletic? To be monophyletic, it has to have all the descendants of a common ancestor. And the common ancestor in a phylogenetic tree, remember, is going to be a node. And practical terms. So it must include all of the descendants of a node to be monophyletic. Mono means one, and the idea here is that this is a true group. So let's look at this. I got this out of the old 101, 102 book, but it shows what we want to see very well. If you ignore the colors, you notice that each of those diagrams is exactly the same. They show exactly the same branching patterns. Well, let's assume, for the sake of argument, even though these are hypotheses, that this is the true branching pattern. This is the way these throughout evolution, these taxa D, E, G, H, J, and K came about. So this is the true relationship. But scientists classify things. They put them into, if these were species, let's say they put them into genera. Which of these three, group 1, group 2, or group 3, would have the criteria meet the criterion of having all the descendants of a single node? Yeah, 1, because B is in fact the ancestor of D, E, G, H, and no one else is. That is a monophyletic taxon. It's not the only monophyletic taxon we could have circled. If we circled F, A, G, and H, that would be monophyletic. If you circle all of it, it's monophyletic, but it has to have all of the descendants of a common ancestor of a node. That's why this type of goal of making monophyletic classifications is why the classifications change so often, more than they used to, because we have more data now. As we'll see in a bit, often I've said things like birds are reptiles. Why would I need to say that? It's because of this goal of being monophyletic. Otherwise, we don't need to worry about such things. But of course, in classification, we try to show relationships. So let's look at what's wrong with the other two, because each of them represents a different type of error. In group, what we have here, does this group include the common ancestor of J and K? Yeah, so it does have the common ancestor of J and K. So what is it failing at? What part of the definition? Yeah, it doesn't have all the descendants of A. That is called paraphyletic. That's the para one. Paraphyly is fairly common, and one of our primary examples that I will use is a well-known example of paraphyletic. But what could cause this type of misinterpretation? Well, when we compare things, often we have to use structures and characteristics, and we're looking for similarities. Would you suspect that the error is that these look too similar to J and K, or are misleadingly different? Which one do you think they are? That they're more different they look more different than turned out to be the case, or they look very similar? Yeah, it represents the fact that the differences seemed so great that it wasn't recognized that they were closely related. And we'll look at well-known example where that happened. The last one is often considered a somewhat more serious mistake, but it's an easy one to make because of the difficulty in telling homoplasies from homologies sometimes. Here, what criterion is being broken? Do we have all the descendants do these even have a single common ancestor that's unique to them? No. So we're violating the common ancestor one, and we don't have all the descendants of any node. That's the polyphyletic. What is likely to cause that error?
Is it if F and I look similar that they think are the same?
Yeah, the J and K there and G and H have a lot of similarities that turn out not to be homologies, but convergent evolution, and it wasn't recognized that was the case. In any event, neither of these fits the definition of monophyletic. Paraphyletic isn't including all of the descendants of the common ancestor. This one doesn't even have a single common ancestor. In fact, if you wanted to have G, H, J, and K, you'd have to circle everything there. If you wanted to have a monophyletic group that included G, H, J, and K. So what about birds? You've often heard that birds are dinosaurs, which means birds are reptiles. But that's not the way they were classified when I was learning biology. And it took a long time for this to become certain. There was always, of course, as there should be, you come up with a radical new idea, it has to be vetted, and people write papers disagreeing with it. Originally it was anatomical and fossil-based. DNA sequences make this quite clear. So if we look at what as best we can say is a true phylogenetic tree, here are the birds, which means birds are more closely related to crocodiles than crocodiles are related to lizards. Notice that lizards are way out over here. Now, true mammals are not part of this clade, but if you look at the clade that includes lizards and crocodiles, it also includes birds. The traditional definition of reptiles, going back a very long time, was that reptiles were lizards and snakes, turtles and crocodiles, and dinosaurs, and things like that. Those are what people call reptiles, and they still do, if they're not taxonomists. Most people, most of us, including myself, normally don't think of birds as reptiles. But in fact, if you want to use a word called reptile as a formal classification, if you want to call something reptilia and say it's a monophyletic taxon, does it have to include birds? Yes. Now, you could simply say there is no taxon reptiles. That would be fine, except that's not the way they do it. That means that if you have reptiles but don't include birds, it's not monophyletic, so what type of phyletic was it? It can only be para or poly, so you have a 50-50 guess. Hopefully it isn't a guess. It's a paraphyletic group because birds, it's not including birds, which are descendants of that node. Why weren't birds included until modern information? Because they really don't, for one thing, they're warm-blooded organisms. They have feathers instead of scales and a number of other characters. Of course, now we know that feathers are not unique to birds, and in fact were quite widely found among dinosaurs, but that wasn't known at one time. And it turns out that although being warm-blooded is important, it's not enough to form their own clade as opposed to, say, that doesn't include turtles and lizards and things like that. It's basically it's a transition that occurred somewhere in here after they split from things like crocodiles and non-avian dinosaurs, probably from non-avian dinosaurs. So the reptile idea turns out to be a paraphyletic idea unless you include birds, which never made either the herpetologist or the ornithologist very happy, but it is what it is. Okay, I already covered that one. So all of this has shown us some of the terminology. So we've seen a variety of different phyletics and morphes and tomes and so forth, which is the way it is. Methods in this field are not something I'm going to cover except for the ones that you will use in your phylogenetic exercises. That is, it may have been mentioned in your textbook, but we are not going to deal with things like maximum likelihood or bootstrapping or any of that sort of thing. You'll use a technique known as the principle of parsimony. Parsimonious principle. And that is basically it's a logical principle. It goes back a long ways in the history of logic. It's used outside of phylogenetics. In a philosophy course, they might call it something like Occam's razor, but we'll call it the principle of parsimony. It has to do with how do you make a decision between two different explanations when you don't have any data that make it clear which one has to be the correct answer. You choose the simpler explanation. It's a logical principle. It's not a rule of nature. Sometimes the more complicated explanation could be true, but if you have no other basis to make a decision, the principle of parsimony says you choose the simpler explanation. That's a principle of logic. It's not a law of nature. It doesn't guarantee you'll get the correct answer, but it's the best tool we have if you have no other way to make a decision. And of course, you can think of many situations where there could be a more complex, and conspiracy theorists always like very complex explanations, but often the simplest one is that there really was just one guy out on a grassy knoll, which was the simple explanation, for a Kennedy assassination, but will never satisfy conspiracy theorists because everything has to be a big conspiracy. Conspiracies are actually very complicated. Doesn't mean they never happen. It's just that you need a little bit more proof than for some things like that. So what about in our situation? Where does parsimony come in? Well, how do people generate phylogenetic trees? They have a set of data. They have, and the one we looked at, of course, was using things like the spots, patterns, and stripes. It could be DNA information. In the first phylogenetic exercise you'll have in this class, you'll be making a phylogenetic tree of hypothetical organisms based on morphology. For those of you who were in my lecture class in 102, you might remember the camilocules. Well, we don't do the camilocules here, but it's a similar concept with a little bit more phylogenetic terminology and so forth thrown in. The second exercise, which will be much later in the semester, will be using DNA sequences to arrive at a phylogenetic tree. So, how do we arrive then at phylogenies? Well, you take the organisms, the groups you're interested in, you arrange them according to a dichotomous branching, and you may get multiple possibilities. Well, the first thing, the principle of parsimony would say in a phylogenetic tree, that if you have to make a choice between two trees, and you have no other way to be sure, you pick the one that has the fewest branches. Fewer nodes, fewer branches. That is the one that has the least number of transitions, the least number of branches. The simplest one. Sometimes, of course, remember this is based on the knowledge you have available to you. When we get better information, sometimes we can decide which one is correct. It may not always be the most parsimonious, but that is only if you have that data that show that. Your textbook has a fairly lengthy discussion, and I'm not going to go through it in detail, but I would recommend it because it takes you through all of this terminology and so forth, looking at what are whales. Whales have traditionally, within mammals, been put in their own order because whales are really, and this includes dolphins and so forth, really very different from other mammals. However, it's been recognized for some time that the whale group does have relationships to what mammalogy people call artiodactyls. This is basically a group of hoofed mammals, and you can see some of them there. It's this type of relationship that led anti-evolutionists to ridicule the idea, well, they're saying cows became whales. That's not exactly what they're saying. But it's certainly showing that a whale would be more closely related to a cow than it is to a tiger. But where do they fit in their relationship to artiodactyls? Are whales simply a type of artiodactyl? Well, they don't have hooves, so this sounds odd. Or are they simply the sister group? Not actually artiodactyls, but closely related to them. And this, of course, was an issue of some interest to people in that field. Your textbook shows how, by a combination of anatomical evidence and genetic evidence, we actually work out which it is. Is it this? Or is it this? Turns out to be this. The whales are actually, if you want to have a group called artiodactyls that's monophyletic, it would have to include whales. Because the closest relative to a whale existing today is a hippopotamus. And hippopotamuses are actually more closely related to whales than they are, say, to pigs or cows. This doesn't mean, of course, that whales descended from a hippopotamus. These are all modern organisms. Now, of course, if you think about it, would you expect that the common ancestor of the hippo or whale would look more like a hippo or more like a whale? Which one seems to have diverged more from the basic plan? Yeah, probably look more like a hippo. Now, not exactly like a hippo, but I'm sure it had 4 legs and all that, and we know that from the fossil record. So, in fact, this is the result of phylogeny. It took more information than was available, say, 20 years ago to resolve it. So in looking at the principle of parsimony and constructing the trees, the data you have are homologies. You have to look at, if you're looking at an anatomical example, like you might in an exercise, you have to look at the characters. You look to see where the characters are, which organisms have them, which ones don't. And you have to try to figure out what tree will allow the evolution of these traits and these different groups most parsimoniously. That's not all that hard to do. It takes some work. It's not all that hard to do when you have a very small data set like we're using. But of course, if you start having lots and lots of species and so forth, do they just do this by hand? No. There are all sorts of methods involving computers and so forth that generate these trees. Remember, parsimony is not the only method used, but they have a lot of different methodologies. But for our purposes, a simple small data set can be done without using computer programs, and it's really not that difficult if you follow in the instructions in the exercise will give you a set of steps on how to do it. Now, since I'm going to have more to explain about this, but I won't be able to do it in 8 minutes. I'll let you all go early today. So in the next class period, we'll finish up with this and we'll start